We'll follow the growth of the waterworks from pre-treatment days when raw river water was used to the complex modern system of today. At the turn of the century, Cincinnati was served by a waterworks which pumped raw river water to a reservoir which is now known as Eden Park. Some of the mud was permitted to settle out of the river water, and mains in the basin of the city were supplied directly from Eden Park. Walnut Hills and Mount Auburn were served by repumping from the reservoir to the higher ground in those suburbs. The water coming from the faucet was so full of foreign material and bacteria that it was the cause of many deaths and several epidemics. In 1897, after an epidemic, the City Fathers established a board of commissioners to study, design, and build an entirely new system. It was decided that raw water must be procured above all contamination from existing city sewers. Furthermore, the proposed water treatment required large areas for settling basins. California, Ohio was the closest location suitable. It was not only upstream of city contamination, but it was also upstream of the polluted Little Miami River. There was ample open ground at a proper elevation to provide extensive settling basins. Having selected a site, the works were designed. The tremendous task of designing and building a waterworks was excellently done by the engineers. Today, the waterworks uses modern scientific methods and is ever alert to the changing times, but the basic plan and many installations remain those of the 1907 design. Let's see what they built, starting in 1898. The intake pier was put on the Kentucky side of the stream near the channel where the water was deepest. From this intake pier, the water flowed by gravity to the river pumping station through a tunnel blasted out of solid rock 60 feet beneath the bed of the river. The tunnel is 1,425 feet in length and 7 feet in diameter. On the Ohio side, the river pumping station housed the triple expansion pumps which lifted the water to the settling basins above Kellogg Avenue. These 4 pumps, each with a capacity of 30 million gallons per day, were of the piston type and were 104 feet high, the tallest pumps of their type in the world. They weighed 2,800,000 pounds. These pumps were installed in the early 1900s and remained in service until 1963. In the 1950s, some small electric pumps were installed to take care of the peak summer loads. In 1963, a second river pumping station, subsurface intake pier, and tunnel were put into service. The new station is equipped with 4 electric pumps, each with a capacity of 70 million gallons per day. This made obsolete the original steam pumps which had served so well. The small electric pumps in the old station now operate in conjunction with the larger pumps. As the water is pumped to the settling basins, chemicals are added at this new chemical building put into service in 1962. Here chlorine, a multi-purpose chemical, is added to the raw water. Its use at this stage is primarily one of taste and odor control. Alum and activated carbon may also be added at this point. In 1909, chlorine was used occasionally for algal control. Since 1915, it has been used continuously to control germs and bacteria as well. The process of sedimentation, coagulation, filtration, and chlorination was then considered the ultimate in the treatment of water. Today, the basic principle remains the same. These are the settling basins. You will notice that there are 2 separate basins rather than one large one. They were so designed to ensure uninterrupted service. When one basin is emptied for cleaning or repair, the other provides a steady water supply. These scenes show the cleaning of one of the basins. The depth of the accumulated silt will give you some idea of how much sediment is removed from the raw water in the first treatment. These basins are large enough to serve our system for another 10 years. Located amid the greens and fairways of the California Municipal Golf Course, all on Waterworks property, the 2 basins have a combined capacity of 350 million gallons. Water is retained here for a period of from 1 1/2 to 3 days to permit silt to settle out prior to more advanced chemical treatment. These are the effluent tubes in the settling basin. They take the water from near the surface, where it is clearest, rather than at the bottom where silt is settling out. Buoyed by drums of air, they are chained at a fixed depth. From the settling basins, the water passes through the chemical house. The addition of each chemical has one or more objectives. Laboratory control indicates what, where, and to what extent the various treatment chemicals are used. Iron sulfate and at times aluminum sulfate are used for coagulation. Lime and soda ash alter objectionable mineral properties. Activated carbon is used for taste and odor control. Ammonia changes the chlorine activity of the finished water. Leaving the chemical house, the water flows to the coagulating basins over the hydraulic jump. The turbulence created here mixes the chemicals throughout the water. In the coagulating basins, the fine silt, which has not been deposited in the settling basins, is formed into larger particles called flock, which are removed here. In normal operation, the coagulating basins are full of water, and most working parts are hidden, as you see here. This will give you some idea of what is behind the scenes, or rather, under the water, in the coagulating basins. A coagulating basin consists of two parts: a flocculator, which houses the large rotating paddle wheels that keep the flock in suspension so that it may grow to a size which is heavy enough to settle out in the second section, the clarifier. The clarifier constantly cleans the bottom of the basin by scraping the precipitated flock into the center post, where it is drawn off by pumps. These basins are self-cleaning. Nevertheless, they are drained and flushed at 6-month intervals. After the water leaves the coagulating basins, it flows to the filter house, where it goes through what are known as rapid sand filters. These filters are of unusual interest. In the early 1900s, a new type of sand filter, the American or rapid sand, was conceived. Research work started at a Louisville testing station and continued at a similar Cincinnati station. On the basis of these tests, the new type filters were installed. We have visitors come from all over the world to Cincinnati to see these filters. Any local group may be shown through the entire installation simply by calling for an appointment. The filtration process is the third step in the purification series, from which 90% of the impurities have been removed by preceding treatments. This filter has just been washed and is being put back into service. The filter beds are made up of 14 inches of gravel beneath 30 inches of sand. In the laboratory, the chemists are constantly testing the water. Samples are taken at various stages of the treatment process. While the bacteria count is of the prime importance, a chemical analysis also records the hardness of the water, the amount of natural chlorides and fluorides in the water, and many others. In addition to the water being tested at the source, samples from various points throughout the distribution system are regularly tested to determine the quality of the water at delivery points. As the water leaves the filters, it is collected in the clear water basin located under the grassy plot shown here, where, if needed, it can again be chlorinated. From the clear well, it flows by gravity through a tunnel 7 feet in diameter to our main pumping station on Eastern Avenue, just past Torrance Road. This tunnel has a carrying capacity of 120 million gallons per day. The main pumping station was originally equipped with large pumps of the same type as those shown at the river pumping station. These scenes from inside the modernized main station show the control panel and the electric pumps, which were installed in 1955. Each pump has a capacity of 30 million gallons per day. In 1952, a second tunnel and a second pumping station were added to the system. Both the tunnel and the pumping station have a capacity of 150 million gallons per day. The Tennyson station is electrically powered. This chimney-looking affair is the terminus of the gravity tunnel and serves as a surge chamber to control water hammer. The main station and Tennyson station are both equipped to pump to high or low distribution systems, directly or indirectly, so that all areas are doubly protected in any eventuality. With this modern control panel, the operating engineers may check, at a glance, the pumping activities through the entire system. The Tennyson station has been equipped with the same type pumps as the main station. From the pumping stations, the water enters the various distribution systems through 3,500 miles of pipe. In the eastern hills, the pressures are dependent upon the height of the water in the eastern hills tanks in Kennedy Heights and the eastern hills reservoir on Winton Road. These two sources of supply are each 275 feet higher than the central system, which makes for greater water pressure. To retard the growth of algae and to eliminate airborne bacteria, the 35 million gallon Winton Road reservoir was covered early in 1957. Shown here are some pictures from that construction. You will note the forest of steel scaffolding which was required to support the roof while the concrete was being poured. In addition to Kennedy Heights and Winton Road, a tank on Cougar Mill Road in Kenwood, and a pumping station and underground reservoir on Zinsel Avenue and Kennedy Heights were added to the Eastern Hills system. And later, an elevated tank was constructed on Conray Road in the Brecon and Blue Ash area to help maintain water pressures in those areas. The Western Hills system is supplied by water repumped from the central service via the Queen City pumping station, which was electrified in 1937. Pressures in the Western Hills are dependent upon the height of the water in the tanks on Ferguson Road in Price Hill, the tank on Wardall Avenue in Westwood, and the tanks in Mount Airy at North Bend and Coleraine Avenues, which are so familiar to most of us. The long-range program to cover all open-treated water reservoirs reached another milestone when the last of the Mount Airy tanks were covered in 1963. The small tanks had previously been covered with aluminum, but the span of the large tanks required the use of pre-stressed concrete beams to support the concrete covers. As the water distribution system expanded, a pumping station on Winton Road near Finneytown, a pumping station and underground reservoir in Summit, and finally, an elevated tank on Kemper Road in Pleasant Run were added to the system to improve volume and service. Here the workmen are constructing the floor of the 5 million gallon reservoir, part of the Summit Station on Glenway Avenue. Of particular interest are the gasoline-powered carts used to deliver the concrete. Here the floor and walls have been completed, and despite inclement weather, the men are pouring the concrete piers which will support the roof. The completed reservoir is completely hidden and is part of the Western Hills playfield. In the central system, pressures are dependent upon the height of the water in the Eden Park reservoirs. In 1962, the work of covering the Eden Park Reservoir was begun. Plans called for the abandoning of the East Basin and increasing the height of the remaining West Basin by approximately 10 feet. This created a reservoir with a capacity of 60 million gallons and raised downtown water pressure by almost 5 pounds. A small mirror lake on top of the covered reservoir was designed to maintain the aesthetic values of the original installation. In 1939, the tank on 3 Mile Road and the Mount Washington tank were constructed simultaneously. The Mount Washington tank was part of the Eastern Hills system until 1951, when the Mount Washington pumping station was built. These construction pictures of the Mount Washington tank illustrate the pre-stressed type of construction utilized, which was a relatively new idea when this tank was built. Here, the concrete inner core has been constructed, and the workmen are now positioning the reinforcing steel bands preparatory to pouring the second course. This is the second of 3 walls which were poured to contain the water in this tank. The small tank, which was originally built in the Cherry Grove area in an effort to supplement the water supply in that area, was replaced in 1961 by a new low-level tank along with a pumping station and an elevated tank. This combination resulted in a pressure increase of approximately 30 pounds and enabled the waterworks to adequately serve the high ground in Cherry Grove and the surrounding areas. In January of 1955, the city and county signed a 30-year contract which paved the way for the $30 million capital improvement program. The bulk of the improvements to be in and for the county areas. Improvements were immediately begun based upon a peak demand of 200 million gallons by 1965, more than double the average daily consumption in 1954. In addition to the improvements in pumping and treating facilities, many of which we have shown you, it was necessary to install many miles of transmission mains. To the west, mains were installed in Pedretti, Delhi, and Neeb roads, as well as Cleves-Warsaw Pike, Anderson's Ferry, and Muddy Creek roads. A new main was installed in Westwood Northern Boulevard, Race Road, and in Bridgetown Road to serve Bridgetown, Mack, and surrounding areas. Water mains in Coleraine Pike, Jessup Road, Cheviot, North Bend, and West Fork roads were installed for the Mount Airy, Montford Heights, and Groesbeck areas. All these new services required additional water being made available to our Western Hills pumping station on Queen City Avenue. Therefore, a 48-inch main was laid from downtown to Spring Grove Avenue via the old rapid transit tube under Central Parkway. In the rapid transit tube on the site of the old Erie Canal, the 48-inch concrete pipe was delivered and positioned with a Ross carrier, which had to back out the entire length of the tube after each delivery. The limited space and the large size of the pipe and fittings made working conditions very awkward throughout this entire project. To the north, additional water was needed in North College Hill, Mount Healthy, and adjacent areas. Large mains were laid in Winton Road, Hempstead, Daly, Compton, Mill, and Waycross roads to supply those areas. In Compton Road, it was necessary to install a portion of the main under the bed of a creek. This called for concrete culverts, a concrete chamber, and a water main laid in concrete. In the valley, mains were laid in Springfield Pike through Wyoming and Woodlawn to Glendale-Milford Road. The Mill Creek Valley was also bolstered by the installation of large mains in Ridge Road and in Reading Road to Evendale. The installation in Ridge Road posed some unusual problems because the main was to be laid under the right-of-way of the cross-county highway, which in turn was to go under Ridge Road, which would be supported by an overpass. This meant that the main had to be laid approximately 22 feet deep at this point through shale, the contractor's nightmare. It was necessary to drill and blast this entire cut. Here the men have drilled the holes, placed the charges, and are now stringing wires preparatory to blasting. The northwest sections of the county, including the High Point and Brecon areas, were inadequately supplied. Therefore, large mains were installed in Montgomery, Blue Ash, and Kenwood roads to supply those areas. In the southeast, mains were laid in Burney Lane, Salem Pike, and Beachmont Avenue, as well as Corbley and Newtown roads. In 1963, work was begun on the well fields in the Great Miami Valley near Ross, Ohio. Plans called for several large wells, a filter plant, and pumping station. The green lines on the map represent the large mains carrying water from the new works to the distribution system. This view of the map shows how most areas in Hamilton County have been aided by the expansion program. Future mains, represented by the blue lines on the map, graphically illustrate how the waterworks plans to encircle the contract area with transmission mains and serve virtually all of the county east of the Great Miami River. While the water itself is free, the service and purification costs money, so we must pay water bills. The billing and collection of those bills is the function of the commercial division. Before the bills can be computed and mailed, the meters must be read. These are the men who do that important job. The uniforms were designed for comfort, service, and uniformity of attire so that consumers may readily recognize a waterworks representative. These men take over 600,000 readings every year. Majority of the meter readers cover their routes on foot. Automobiles are used to obtain readings in widespread areas. This is a watchdog. He's watching the man work. This is what is known as a Ford meter box. It is a frost-proof box installed outside so that it isn't necessary for the man to enter the house to read or service the meter. These are known as remote registers. With these devices, the meter remains in the building, but the reading is obtained from outside. Administrative, distribution, and commercial division offices are located at 4747 Spring Grove Avenue. In the commercial division will be found the cashier's cage, where you may pay your water bill in person. However, approximately 90% of the bills are paid by mail. The commercial division is the business office of the waterworks. In this division are maintained over 168,000 active accounts. Here the many clerks perform every business activity, such as checking readings, ordering investigations, computing bills, warning customers of excessive consumption, and answering customers' calls, questions, and occasional complaints. Applications for most services are made to these clerks. Some come in the mail, although most are phoned. In a year's time, close to 100,000 requests are received. The Waterworks makes it easy to apply for water service. No signatures, guarantees, or deposits of money are required. However, the property, rather than the individual, is held responsible for water bills. These are water meters, sizes 1 1/2 inch, 1 inch, 3/4 inch, and the 5/8 inch meter used in most homes. This is the IBM room. Here your bill is actually prepared. Cards are punched and bills are printed. The girls are using the card punch machines. They punch the information into a card, which is later fed into the accounting machine, which interprets the information on the card and prints it on your water bill. Here you see water bills being printed prior to mailing to your home or business. These are the processed cards, which were originally prepared by the card punch operator. This is the sorter. This will sort out automatically any group, series, or combination of series which might be needed for reports or statistical purposes. This employee is wiring a control panel for the accounting machine. This panel tells the machine how to proceed and exactly what functions to perform.